All right, so yesterday at the end of the video, we saw the solutions, the zeros to this equation. So we had -3, and 3 halves, and we didn't get to do the graph. So I want to talk about that real quick, and and especially kind of highlight what's going on. Why do we have this same zero twice? You don't normally see that have the same answer twice. So let's go ahead and think about what the graph is going to look like. So in context of what we've been talking about. So we know that one of the zeros is -3, so I'm going to put a point over there on the left side at -3, wherever I think that is, and I have another point at -3. So I'm just going to put a point on top of that one, right? That's also at -3, and then I have another one at 3 halves, which is equal to 1.5. So kind of somewhere in there, 1.5 is. So there's my x-intercepts, and my zeros. So let's go ahead and look at Desmos and see what we see from that graph. So it looks pretty similar to the graphs we saw yesterday. There we confirmed that our zeros are right, -3 and 1.5, the 3 halves. But it does look a little different because the graphs we saw yesterday were all n-shaped, but they were normal, and this one's kind of an upside down n shape. So what's up with that? Like, why is this upside down? The left end points up and the right end points down. And something else that's different is that this graph is acting weird at -3 there. Don't really see that where it like almost looks like it's bouncing off the x-axis rather than over here at this x-intercept where it's passing through the x-axis, which is what we're more used to seeing. So what's going on there with this -3? Why is it bouncing? So, but let's draw a quick sketch. So it looks like an upside down n. So as I draw it from coming down from the left side, and then bouncing off the x-axis there, and it bounces pretty far up, and then comes back down, and then passes through there on its way down forever. So arrows on both ends, then that bounce there at 3. So kind of the easier thing to address is this. Why is it upside down? Right? Why is the graph upside down? Why is the left end going up and the right end going down this time? Well, I think it's not too big of a mystery that there's a negative here on the front of the graph, and we've seen that over and over again. What negatives do to graphs, that they turn them upside down, so they reflect them. So there you go. Why is it upside down? Because the first term is negative. So it shouldn't be too surprising. First term is negative, so graph's upside down. It's maybe a little bit trickier to figure out is why is there a bounce here? So why is there a bounce at x equals -3? And so what that does deal with is that idea that there are multiple answers of that same x equals -3. And so what this is called is multiplicity. So how we say this is that x equals -3 has a multiplicity of 2. So it may seem like a kind of a scary word, right? A big word, multiplicity. Ooh, what's multiplicity? At its core, multiplicity is really simple. How many times does that number show up as an answer? -3 shows up twice as an answer, so its multiplicity is 2. So in that same way, x equals 3 halves has a multiplicity of, well, how many times did 3 halves show up as an answer? Once. So it has a multiplicity of 1. So if I'm asking you to tell me about the multiplicity of a 0, all I'm asking you to tell me is how many times does it show up as a 0? -3 showed up twice, so its multiplicity was 2. 3 halves showed up once, so its multiplicity is 1. Okay? That's it for how you tell from the answers what the multiplicity is. How that's connected to the graph is a little bit more complex. Okay? So as we look at that answer that has a multiplicity of 2 and how it is acting how the graph is acting at that point, right? Normally we see the graphs passing through those x-intercepts. Okay? So anytime there's a multiplicity of 1, we see that pass through. And so if we look at one of our older problems, each of these zeros only showed up once. They all have a multiplicity of 1. Each of these is passing through, the graph is passing through each of those points. Nothing really weird is happening there. And same thing on this graph. each of those zeros only showed up once. So we see that the graph just kind of passes through each of those points, like we normally would think. Okay? So what we're seeing though is that if the multiplicity of the 0 is 2, the graph appears to bounce off the x-axis at that point. So it's something we just want to make start to make a visual connection with, that a multiplicity of 2 creates a bounce. Multiplicity of 1 creates just a pass-through situation. Okay? We're going to keep talking about multiplicity as we go through more examples, but it's kind of an introduction there. I just kind of condensed the instructions a little bit. We're doing the same thing here, finding all the zeros. We are also going to make a sketch, and we're also going to discuss multiplicity. Okay, did add that to the homework. Forgot to add it to the notes here, but we're going to do that. So we are given our function, and I also did forget to put the little f of x equals here, but that's not a big deal. Okay. So f of x equals 9x to the fourth plus 27x cubed minus 16x squared minus 48x. There's no constant there at the end. That's weird. So that actually does need to be addressed. There's no constant. So there is a gap there, and then we would add 0 onto the end of that problem. So it's a little weird that there's a gap at the end of the problem, but it is missing a term. It goes 4, 3, 2, 1. And it never hits 0. So we put that 0 in there as a placeholder in our problem. Okay? Where the gaps are there is placeholders. It's missing the constants place, so we need to put something in that place. We can't put a number because that would change the problem. We can put a 0 in there without changing the problem. So I'm bringing down all those coefficients along with that 0. Okay? Bring my little half box. And then I'm going to bring that -3 over. Remember, I'm not switching the sign because I'm giving you guys the 0 there, so we don't switch the sign. We use the number that I'm giving you. Okay, so, this problem is bigger than some of the ones we've seen, right? It's got 9x to the fourth here, right? So fourth power as opposed to a cubic that we had been talking about. So this problem is going to have 4 answers, not 3. Okay? I'm giving you one of them, so that means you need to find the other 3. Okay? Start by dropping that first number. So 9 times -3 is -27. Add that down, you get 0. -3 times 0 is 0. Add that down, you get -16. -3 times -16 is 48. Add that down, you get 0. 3 times 0 is 0. Add that down, you get 0. Well, that's kind of weird to get 2 zeros at the end. But in the end, right, we wanted 0 to be at the end, and well, there's our 0. So there's our first little built-in check. Are things going well? We plugged in -3, or we divided out -3, and we got 0. Yes, things are going well, right? Remember, I gave you a 0, you better get 0. Okay. Where do we go from there, right? Remember, that's our remainder, our constant, our x squared, our x cubed. So as we put those x's back into the problem, write that resulting polynomial is usually how I call that. So this would be 9x cubed. And then I have 0x squared, so I'm not going to write that there. Then I have minus 16x's. And then I have 0 constant, so I'm not going to write that there. But we do always want to set these equations equal to 0. Right? We're going to bring down our numbers here, put the x's back in, set it equal to 0. Bring those numbers back, put those x's back in, set it equal to 0. Okay? The x's back in, set it equal to 0. All right? That's what we're doing here. So we write that resulting polynomial and we set it equal to 0 so we can solve it. So at this point we want to be looking at this equation here and asking ourselves, how do we solve this? Right? How do we solve that? Well, we're talking a lot about factoring, right? Always want to factor. Factoring is going to help us get x's by themselves. Well, what type of factoring do we always try first? Right? We should always look to see if there's a GCF. 9x cubed and 16x, those both have an x. So let's get that x out of there. So that'd be 9x squared minus 16. That would equal 0. Okay. So are we done factoring? Is that all the factoring we can do? So you look inside the parentheses, ask yourself 2 questions. If there's anything in common, which there is not. And then are there any higher powers? Ooh, but there is a higher power. So that means we need to look inside at that 9x squared and minus 16 say, can we do more? Okay. And you should recognize this, right? It's got two terms, it's got a subtraction, and both of those terms are perfect squares. 9x squared is a perfect square, and 16 is a perfect square. So this is going to factor into a difference of squares factor. You guys really do need to see that quickly, that see a difference of squares, recognize it, look at something like that, and go, oh, that's a difference of squares. And two terms, subtraction, both are perfect squares. And whenever we factor difference of squares, we always get one positive factor and one negative factor, or one factor with a plus in it, one factor with a minus in it. And then other than that, they're exactly the same. Right? So we ask ourselves, well, where did 9x squared come from? Well, it came from 3x and 3x. And then where did 16 come from? It came from 4 and 4. So, right, so recognizing a difference of squares, factoring, so you can do it quickly. You could also do the AC method there, but the difference of squares is much faster. Now we're done factoring because there's nothing left in common, and there's no more higher powers. So now we set each of our factors equal to 0 so we can solve. First one, don't forget about that x equals 0. And then 3x plus 4 equals 0, so you're going to subtract x over and then divide by 3. So subtracting 4 divided by 3, so negative 4/3. And 3x minus 4 equals 0, so add 4 over, divide by 3. So positive 4 over, divided by 3, positive 4/3. And don't forget about the original 0 I gave you, x equals negative 3. So here are the 4 zeros to this problem. Right, so there should be 4 answers. There are my 4 answers. It should always be something that you check, like kind of when you think you might be done. Right? Do I have the right number of answers? There's supposed to be 4. Okay, I do have 4. Or there's supposed to be 4. Ooh, I only have 3. Something's not good. Or it's supposed to be 4. I have 5. Right? So just kind of quick check. Does my answer? Do I have enough answers? Okay. Then we're supposed to sketch a graph. So let's think what that looks like. So I've got a negative 3. Somewhere over here is negative 3. Got a 0, so that means I'm at the origin. 0. I've got negative 4/3. 4 divided by 3 is 1.333. So 1.3-ish, negative 1.3-ish. Then 4/3 is positive 1.3-ish. All right, so there's my x-intercepts. What's the rest of the graph going to look like? So let's look at the Desmos. Okay, so here it is. So we can kind of see what shape we're looking at here. If you notice, this one is not an N shape; it's more of a W shape. So I can zoom around here. Okay. How do I know if my answers are right? I'm going to click on those x-intercepts. Negative 3, 0. There's that negative 1.3. That's the negative 4/3. There's that positive 1.3. The positive 4/3. So our answers are right. So we get a nice little confirmation there. We get an idea of what's going on with this graph. And so what I'm seeing here is kind of a wibbly wobbly wonky 0. Oh, W. Sorry, wibbly wobbly wonky W. Okay, both sides go up. So you want to pay attention to. Both sides go up. Undulates in the middle. Okay, as I draw this. So coming down from the left side. Now remember that left one did go down further between the two, so I'm just going to draw it a little bit further. Comes up, back up. Bounced back down towards the 0. Did not go down quite as far. And went up forever. Okay. So that's what our graph looked like. What I noticed at each of those x-intercepts, the graph appeared to just pass through each of those points. Nothing really weird was happening. Right? What that deals with is the multiplicity. Each answer only shows up once. So that means they all have a multiplicity of 0. So I'm okay if you say that. You don't need to write each one out since they're all the same. You just want to say they all have a multiple 0. Or maybe instead of saying they, maybe say the zeros. The zeros all have a multiplicity of 1. I feel like I said they have a multiplicity of 0 earlier. I hope I didn't. That is not a thing. There's no such thing as a multiplicity of 0. So the zeros all have a multiplicity of 1. Each one shows up one time. And then they all pass through. The graph passes through each of those points smoothly. Okay? So there's finding the zeros for that one. Saw some different things there. One more example. Same idea. We're going to talk about multiplicity again. Forgot to write that there. Okay. I'm giving you guys the 0 again. So x equals 2. On a glance at our function, again, I forgot to put the little f of x business there. Not too big of a deal. So guys, look at that function, x to the 4th, x squared, no x's. Ooh, we got something weird going on here. There's no x cubed term. There's also no x term. So we have multiple gaps here. Okay, so that's the first for us, but that's okay. You can have multiple gaps. So across the top of my box, I'm going to write 1, 0, 5, 0, negative 36. 2 was the number we're going to divide out. Do not switch the sign. Bring the 1 down. 2 times 1 is 2. Add down, you get 2 times 2 is 4. Add down, you get 9 times 2 is 18. Add down, you get 18 times 2 is 36, which is awesome because that means we did it right. First check, right? Did our synthetic division right? 2 gave us 0, right? If you had not put those gaps in there, if you forgot both of them, if you forgot either just one of them, you would not have gotten 0 there. Right? It would tell you that you're doing that wrong. What do we do with that? Right? We put those labels back on. R, C, X, X squared, X cubed, getting bigger as we go to the left. Then once we have it labeled, we rewrite it as x cubed plus 2x squared plus 9x plus 18 equals 0. Make sure you set it up as an equation. You cannot solve it if it's not an equation. Well, how do we solve it? And speaking of, how do we solve this? Well, last time we were able to factor out a GCF and then do some difference of squares factoring. So we're factoring. Oh, do I have a GCF? Nope. Can I do difference of squares? Nope. Right. Can I do AC method? There's 4 terms. Can't do AC method on 4 terms. Can't do AC method on a cubic. Okay. How do we factor 4 terms, right? There's the kind of the key thing here. How do we factor 4 terms? Well, if you remember, that's the grouping method. So we cut it in half. Those both have an x squared in them. Leaves me with an x and a positive 2. The next 2 terms both have a 9 in them. That leaves me with an x and a positive 2. So there's your second little built-in check here. Oh, things are going well. Okay. So once we know that those things are going well, we say our x plus 2's go together. And then those leftovers go together. The x squared and the 9 go together. And here's our, what we hope is our done factoring. Check though. Anything in common? Nope. Any higher order powers? No. Anything in common? Nope. Any higher order powers? Yes. So, there might be some more factoring here. Then we go, oh look, it's 2 terms. It's perfect squares. And subtraction. Oh wait, that's not subtraction. 2 terms, perfect squares, subtraction, difference of squares, factoring, 2 terms, perfect squares, subtraction. That's not subtraction. So I can't not do difference of squares factoring, right? Difference means subtraction, okay? So we cannot do that. Well, if we tried the AC method, my A value is 1, my C value is 9, our B value is 0. So 1 times 9 is 9. Any factors of 9 that add to be 0? 3 and negative 3, of course. 3 times negative 3 isn't 9. Okay? Factors of 9 that add to be 0. Well, 1 times 9 is 9. Can't get 0. Negative 1 times negative 9, 9. Can't get 0. 3 times 3, can't add those to 0. Negative 3 and negative 3, can't add those to 0. There are no factors of 9 that add to be 0. Okay? So this is not factorable. So it turns out we cannot factor that. So no more factoring. So if we're done factoring, that means we have to move on to solving. So x plus 2 equals 0. So that means x equals negative 2. X squared plus 9 equals 0. So we're going to subtract that 9 over. X squared equals negative 9. And then square root both sides. Get rid of the square. X equals, well, what happens when we square root 9? Square root of 9 is 3. How does we square root of negative 9? Negative 3? No. Okay. Square roots of negatives are imaginary. Square root of 9 is 3, so square root of negative 9 is 3i. Okay. Square roots of negatives are imaginary. Did you remember that? Okay. What else happens when we square root? Okay. Remember that there are supposed to be two answers to this question right now, positive answer and a negative answer. So did you remember there's a plus minus here? So a couple things that you might have forgotten as you're solving. Do you remember there's a plus minus when you take the square root of both sides? Do you remember that when you square root negatives, you get imaginary numbers? Okay. Don't forget about our original answer that we had, x equals 2. Okay. So I'm just going to write this in a little bit neater list. I guess I'm going to get stuff all over the place. So we're supposed to have 4 answers. We got x equals 2. We got x equals negative 2. We got x equals 3i. We got x equals negative 3i. So 4 answers. Okay. 4 answers like we thought. What's that look like on the graph? How do we deal with 3i on the graph? I think of this one, 2. I know where 2 is. There's 2. I know where negative 2 is. Negative 2. Well, maybe we need to look at the graph to figure out where 3i and negative 3i are. I don't know where those are on the graph. Let's look at that one. Well, here's our graph. There's 2 and negative 2. You can kind of see the graph going way down there to negative 36, but whatever. It does not appear to be coming down anytime soon. So it does not appear to have any other x-intercepts, which really shouldn't be too surprising considering that 3i and negative 3i are imaginary numbers. We would not see them as real x-intercepts. So the graph shoots up on the left side, it should go way down to negative 36, but whatever. It can be back up, shoots up to the right side. So there's our graph, right? Yeah, so a little side note there, right? We just talked about that. The imaginary zeros do not give x-intercepts, right? The real ones do. So we shouldn't see them. And then the last thing we talked about is the multiplicity. So again, how many times does each 0 show up? Well, once. So again, all the zeros have a multiplicity of 1. So it doesn't need to be part of your work for those new problems. It's talking about the multiplicity of your answers. All right, and again, just want you guys to get start getting an idea of what you see. Compare the multiplicity to the graph, right? Again, so what we've seen, you've seen that multiplicity of 1 looks like a pass through. So we see that at negative 2 it's passing through, and at 2 it's passing through. We don't see those, so we can't talk about the graph there. We saw with the multiplicity was 2, there's a bounce. Okay? You guys are going to see another multiplicity. Which I want you to just look at the graph and say, well, what's the graph doing with the multiplicity of 3? So how does the graph look? What word could you maybe associate with that? Bounce, pass through. What's the 3 do? So, all right. hopefully that went pretty well for you. You understand that, but let me know if you got questions. You know where to find me.